Good afternoon, honorable judges and opponents of the report. This is a report to Shitore Company NDPH1. And today I'm going to report about the problem of ping pong locking. And this is the outline of the presentation. This is a problem statement. A ping pong ball is placed in a container of water. When the container is dropped, the ping pong ball will get launched into a great height. What maximum height can you reach with up to 2 liters of water? So our main focus is the maximum height, the container, and we are also going to focus on the amount of water. And this is a demonstration video. So you can see that the ball is placed into a container with water, and then the container is dropped. And then when the container hits the ground, the ball will get launched into a great height. And the picture on the right is a picture of the process of the motion. And you can see that the ball sinks under the water surface. And this is our experiment setup. We use a string to make sure that we had a string to make sure that the container is straight when it falls down. And then we cut the string, and we use a high-speed camera to analyze the motion. And this is our theory. So first, our assumptions. We assume that the ball sinks under water level before impact, just as because as the picture showed in the demonstration video, the ball sinks under the water level. And we believe that the container and the ground are rigid. And we are going to represent the impact time, also the duration, by the symbol tau. And this is what happens during the free fall state. So here, the term on the left means the total force exerted on the ball. And it can be derived from the force diagram over here. And these are the forces when we put the observer in the acceleration coordinate system. And because the acceleration of the system A0 is very close to the gravitational acceleration, so the buoyant force can be neglected, and therefore the ball sinks into the water. And when the system hits the ground, we assume that it is an elastic collision because the vibration due to the elasticity of cup will cause the total energy not conserving. And because when the system hits the ground, the acceleration of the system becomes upwards instead of downwards, so the buoyant force returns. And after impact, we can use the momentum transfer and impulse to calculate the change of velocity of the ball. And this is shown in the equation over here. And by substituting A0 into this term, we can get that the velocity of the ball after impact is approximately 4.19 times the velocity before impact. And then we know the velocity of the ball after impact. We want to know how high we can get to the maximum height. So therefore, we consider the ball only experiencing its weight and the air drag force. And this is the method of calculating the air drag force. So over here, we can then describe the motion as these two equations. One for the ball falling from rest, and one for the ball rising with an initial velocity. And for this equation, by setting this derivative into 0, we can get the terminal velocity over there. And by solving these two equations, we can get these two equations. And because we are focusing on the vertical axis, which is the height of the ball, so we can solve the displacement on the vertical axis, and it is over there, shown in the equation over there. And by simplifying this equation, we can finally get the maximum height the ball can reach, expressed over here. So then we want to find the relation between the maximum height. Oh yeah, this is the equation of height and the terminal velocity calculated over there. And when we get this equation, we want to find the relationship between the initial release height and the rebound height, which is the maximum height you can reach. And by substituting those two equations into this equation, we can get the relation between the rebound height and the initial height. And this is our first experiment. So we are going to focus on the radius of different cups. And we're controlling the depth of water and the initial height. And this is the result. So we can see that from this graph, there is a peak for 4.5 centimeters radius of cup. And we believe that this is the best effect for the ball to launch into a maximum height. And for bigger radius of cups, We believe that is because the surface area is bigger, causing more turbulent flows in the water and causing a lot of energy dissipation. And for a smaller radius, because the radius of ping pong ball is only 2 centimeters, and this will happen when we put the ping pong ball into the container. The pressure difference will cause the ping pong ball to stick to the wall of the container, and therefore there is energy consumption when released. So for our experiments in second and third experiment, we are going to use a cup with 4.5 centimeters radius. And for experiment 2, we are going to change the amount of water. And according to our theory, the amount of water should not really have a great effect on the rebound height, because we are going to be focusing on the velocity after impact and the velocity before impact. And the velocity before impact depends on the initial height, release height. And here we can see that this fits our predicted trend. And for this point, there is a decline, because when the amount of water is only 100 milliliters, the ball will touch the bottom of the cup, and therefore getting another external force acting on it. However, we believe that when the container falls down during the free fall acceleration, the water, as shown in the graph for the demonstration video, we can see that the surface will form into a curve, and this curve will cause a surface potential energy in the water, and this is expressed over here. And the potential energy then transfers into the surface energy. And here, M is the mass of the breaking water, which is only the part of the water between the red lines, which is the part of water that crawls up the wall. And delta H over there is the displacement of its center of mass. And then the surface energy, after the container collides with the ground, the surface will fall back into, the breaking water will push back on the ball. And so the surface energy then transfers to the kinetic energy of the ball. And for our third experiment, we are going to change the initial height. And using 200 milliliters of water inside the cup. And this is the result. So according to our theory, we did only 30 centimeters initial height to 170 centimeters initial height, because there are some limitations in our experiment. So for initial heights below 30 centimeters, the motion is too fast to be observed, so we can't get the accurate rebound height of the ball. And for height bigger than 170 centimeters, the cup will break, so we can't observe it too. And here, the orange line is the trend that our theory predicts, and the blue dots are our experimental data. So according to our theory, it is a natural log function, which is also meaning that the rebound height and the initial height should be in exponential functions. And the experimental data fits our theory, as you can see over here. And this is the overall data of every combinations of different amounts of water and different initial heights. So from our experiment, we can see that the greatest rebound height we can get, which is the maximum height, is when the water is 200 milliliters and the initial height is 170 centimeters. So the maximum height here we get, I forgot to put it here, so it's about 6.5 meters. And this is a conclusion of the overall experiment and theory. So first, according to our theory, the velocity of the ball after impact depends on the velocity before impact, which changes with different initial heights. And second, the surface energy is a potential factor that might affect the rebound height. And the change of surface energy is due to the change of amount of water, because changing the amount of water means changing different mass of breaking water. And third, there is exponential correlation between rebound height and initial height. According to the theory and according to our experiment data, it also fits this trend. And at last, in our experiment, for every combination set we did, the greatest maximum height we can reach is the combination of 200 milliliters and 170 centimeters initial height. And the maximum height is 6.5 meters. And this is the end of my report. Thank you.
Okay, so first I want to ask you a question. First, you said you use a string to stretch the container. Then how do you make sure that when the container lands on the ground, it lands flat on the ground?
Okay, so this is how it works. The string is hand across the container, and then we place the middle of the string. We hand it onto.
Okay. I understand. Thank you. And the second question I want to ask that have you, during your experiment, has the ping pong ball bounced off of the walls of your container?
Bounce off. Well, in our experiment, if it bounces on the wall, we won't take the data.
Okay.
And we'll do it.
Okay, thank you. And thirdly, once the ball is bounced out of the container, do you include the angle of the projection?
Yes, because we use, I didn't mention that, we use tracker to analyze the motion, so we get it.
And fifth, I want to ask that have you thought about like when the container lands on the ground, some of the water may actually be splashed out of the container, and have you considered that? Like not all of the water will stay in the container.
We think that it doesn't affect because what we're focusing on is the collision between the ball and the water.
Okay.
And that happens after the collision.
Okay.
Yes.
And the next question I want to ask is, what do you think is the main force that pushed the ball upwards?
The main force.
Yes, the main force.
Oh, the main force is well, I said after collision, the buoyant force returns, right?
Okay.
And it doesn't really, yeah.
And have you considered the energy transformation from before and after? Like the percentage, how much is transferred into the light?
We didn't.
Thank you. statement, and I think out of the problem statement, I think our main points should be focusing on the maximum. They focus on the main points: maximum height, container, and the amount of water within. So the brief summary of the reporter, we think that the observation they talked about the ball sits under water level before impact, and they talked about the free fall state and the buoyant force when the ball is inside of the water. And the experiment method, they use a string to control the route of where the container will land, which I think there's a little more I want to discuss with you on that. And for the data analysis, the amount of water didn't greatly affect on the height, and the initial height and rebound have an exponential correlation. I will ask for the reason later. And conclusion is the surface energy is a potential factor for amount of water affecting the rebound height, and the greatest rebound height is 200 milliliters and 170 centimeters. And the correlation next. So I think the pros of the reporter is there are clear demonstration of the phenomenon and consider various variables. But the cons is they have a lack of explanation of the results and not clear of how they actually saw the experience. There's no picture for that. And the theory is the theory I want to talk about is the process of the falling and how they ensure the landing. And the experiment method I'll be main focusing is how do you ensure the container will perfectly fit the ground, the falling, and how they avoid the bouncing off the walls, and how do they control the angle, or how do they actually use the height, like how do they calculate the height, and have they talked about like the water actually coming out of the container when landing, and what will cause error if the ball is not in the middle. And for data analysis and conclusion, I was saying that I'll talk about later they forgot the fitting and error bar and after for their reasoning in doing that. And next, I'll be asking how they correlate the theory with the experiment. And for extension, I want to ask is that I'll talk when I get there, and I want to start my discussion with the opponent, with the reporter. Okay. So firstly, I want to ask that. So you said that if the ball bounces off of the wall, you don't take that as
because if it touches the water, it's under force.
Okay. Then can I ask out of how many times, like for example, out of every 10 or 50 tries, how many times would that happen?
Well, the percentage of happening is I didn't remember, but I think that it's about 30.
And how many times?
30%. Yeah.
Okay. So how many times averagely do you do the experiment?
I did it for about 50 times.
So you did 50 times.
Okay.
So that's about 10 or 10 to 20 times. Okay. And you average all of that, like the height of all of the
for
bounces.
one combination of
Okay.
water.
Okay, thank you. And I want to ask for the angle, is that of course there will be an angle in it, and I want to ask that the height is only the vertical, and you don't talk about like the whole ground. Can I use the blackboard?
Yeah, sure.
Maybe before that, I want to ask you a question. Is that how do you think the energy transformation, because before when the ball and the container touches the ground, they will have a potential energy.
Surface force.
Yeah. Surface.
Oh, did you say?
Before everything.
Okay.
So before, so there is an energy. So maybe I call it the initial energy. Then after, maybe it will fall to the ground, and then the ball, I said after everything, it falls. So the ball maybe, for example, where it flies off the sun. So maybe it falls, flies in different direction. So for example, like this. How do you think the energy from here will transfer to here?
Well, of course, very directly, this is the potential energy, gravitational energy.
Yes.
And then the ball bounces off with velocity.
Yes.
So I believe that it's the transfer of gravitational potential energy to the kinetic energy of the ball.
So did your theory talk about something about this?
No, because we are going to analyze it from the motion, not the energy.
Okay.
Because if we focus on energy, there might be some other factors that cause energy dissipation.
So then I want you to focus on, can I, we stayed at the blackboard, and can you turn to page number 7 or 4? Whatever. Maybe page number 7. Okay, so here I maybe turn to 4. Okay, so from the picture on the right, actually I want you to draw. Can you draw like the process of how from the ball from here to here? Can you draw the process of the whole, like how the ball?
What it looks like.
Yes.
From the inside looks like.
Yes.
Okay, so this is the space like that. Before, and then when it starts to fall, the container, it has an acceleration, and then this is in the equilibrium stage when the water surface is horizontal, and then the surface will then slowly form a curved shape like this, and then because as we said, the lack of body force, the ball will sort of sink inside, and then this is a free fall state, so when it touches the ground. There is a phenomenon, well, we can call it a water jet, something like water. And when it hits the ground, the ball will be bounced out with auxiliary to the velocity after impact. And then the surface, the curve of the surface collapses.
So you think it is, so can you tell me where the buoyant force acts in this process?
Okay, so
can you draw the buoyant force like this? Can you draw the buoyant force from here?
So when in free fall state, the buoyant force is nearly zero if we put our observer in the acceleration coordinate system because of the measuring force due to this acceleration.
Okay.
So this buoyant force here is bigger. And then after it hits the ground, the acceleration is no longer downwards, it's going upwards. Right?
So
this is after correction.
So where's the buoyant force? I'm asking for the buoyant force.
So it's like there's still the little part.
So you think it's only this little part, and that we call this?
Yeah, because buoyant force is the part of the fall example.
Okay. Well, in my opinion, I think that the process should, because from that picture, I think it's
well, that picture is before it hits the ground.
Yes, I know. So it looks something like this. But I think the buoyant force, this much buoyant force, I think it should be looking more something like because the height of this water. So the upper part, it will close together faster than the bottom. So it will look, there will be like a minimal air gap on the top, looking something like maybe the water like this. So this is air. So I like from here, and the water flows in like this, and then so there will be air gap here, and because of the pressure difference, so the buoyant force acts like this, not just this little part. And what do you think?
Yeah, I think that's correct. But actually, I think that this is actually talking about like another like 0.001 seconds before this state.
Then do you think this part's buoyant force is bigger than this, or do you think?
Well, of course not, but as
then do you think
yeah,
this
is the
main reason?
This is the biggest buoyant force, right?
Yes.
So and then as it goes out, the buoyant force gets more and more, right?
But so you think calculating from here to here is important? Like calculating buoyant force from here to here is important.
Yeah, but we are not calculating the buoyant force in the back.
Okay, thank you. Can I ask for page 15?
Yeah.
Can I ask?
Error bar.
So you didn't forgot.
Yeah, it's.
Okay. It's fine.
Sorry.
Okay.
Sorry.
No, it's fine. Then can I ask for page 18? Can I ask for the reason why the amount of water in 50 is not measured? Like why is there no dot on it?
because for amount of volume 100, the ball already touched the bottom of the cup.
Then do you think that you can change? Like for example, of course you're talking about amounts of water. Then can you do another experiment that has maybe different kind of container that is maybe different
That's
radius?
in our first experiment.
Yes, I say no. I mean different amount of water, but in the same container. Maybe like that. Maybe the radius you did was like 20 centimeter. Maybe you use a 10 centimeter radius container, so the water will be higher and it won't hit the bottom. Do you think that's viable?
Yeah, it won't touch the bottom, but from our experiment one, our result is that the best effect is a radius of 4.5.
So you only want to talk about this?
Yeah, so we're going to focus on
Okay.
4.5 because we want to maximize the rebound height.
Okay.
That's what
Then
the policy is.
can I ask for page 21? Page 21. Can I ask for like the exponential correlation? Like where in the formula did the exponential correlation come from?
Okay, so from our theory, and as we get this function of the, actually I can show this one. The last one we got here. So this is the maximum height in cat, right?
Yes.
And you see a natural log here. And
Okay.
the initial height is inside the natural log.
Can I ask the question is that what do you think that will cause the correlation? Like where does the natural log come from? Why is there a natural log inside of the?
Because by solving this one and this one.
So what is solving those two mean in physics? Like what are you doing there?
These two equations are from these two because after the ball is launched into the air, we only focus on the drag force and the weight of the ball. So analyzing these two forces exerting on the ball, we can the motion can be expressed by these two sort of functions or equations.
Also, so you derive the natural log from those two equations.
Yeah, from solving these two equations.
Okay. Then can I ask for the page where you say the max, like the graph where you show the max, like the max height?
Or this one?
Yes. So can I ask for like why, like for example, like there's only 20 meters and 170 centimeters. Like have you tried on like things that are like for example maybe a higher height or larger amount of water?
Well, so for higher heights, we said that our limit is to 170 centimeters.
So you said
So above 100,
okay.
yeah.
Then what about the volume?
The volume of water is done over here. So we can see that although it does not change much, it still varies, right? Like in our range of.
So you pick a random amount of volume?
No. It's still according to our raw data. We still get a bit, but because this does not really.
So did you say that 20 is the 200 is the highest?
Yeah. 200 and combined with 170 centimeters initial height.
So you didn't change other types of volume, like don't change 170 with 100 milliliters of water.
170.
Like because you said it doesn't change as much, so I thought if you could try out different.
Yeah, it's okay.
So I think you can try out
different colors of dots means different amount of waters.
Okay.
Yes.
So to conclude the discussion, I think that firstly our main topic is talking about how they control the landing, which I think talking about how the time scale did the experiment, which we think that of course the ball will bounce off the wall, but I think doing more experiments can ignite that factor. So and second, we talk about how the buoyant force actually forms, which I think that the buoyant force that we talked about should be larger than what they talked about. So we think that our buoyant force it should be the main reason why the ball should bounce out of the water for such a high height. And lastly, we talk about why how did they measure the maximum height, which we think that they should do. They can actually try using another container and trying more data results to try for the maximum height.
I want to add what is the main factor to cause of the ping pong ball that switch.
Okay.
Before the first. Why? Why the ping pong ball will drop like?
Well, because it hits the ground and then the return of the buoyant force causes the water to push back on the ball and the ball will go out and push back.
Okay.
Well, I think that because the ping pong ball, when it lands, so it pushes the water apart. And once the water wants to form back to its original state, it produces the sum of the force will go up and will push the ball out of the water.
And the next question I want to ask, how to get the maximum height?
How to get the maximum height? So,
What factors determine the maximum height?
so I think the main factor from our experimental results is initial release time.
Okay.
I agree with the reporter. We think.
And the next question is I want to ask the reporter. You say that you do the experiment 15 times, right?
Yeah, about 50 times.
So why your error bar looks really small and seems like every point has the same error bar value? Why?
This is the one for the initial height and
Okay.
because we did a lot of times and we averaged the value, so there should, like, the more times we did, the less the error will be. And after we average it.
I think your error bar, every point looks like the same. So, let's go to the next question. And the next question is, why the water is important to that this phenomena happen? Why we have to use the water? Now we use the solid other thing. Why?
Because the amount of water, because if the ball, well, the difference is that the ball only touches it's two solid bodies colliding together. But with water inside, water is a fluid, and therefore there will be other dynamic forces affecting the causing the ball to get into the impact.
We think that we think that the reporter is partially right. We think that fluid has some fluid hydrodynamics that will actually affect the height.
Okay. container was vertically in the ground by using a rope. And for causing, it had a device used rope, but the reporter didn't consider the rope taken in the theory. And for the data analysis, he got the natural height and other parameters, and first he had a quality comparison between the theory and instead about the initial velocity. About the natural height and causing actual error bar in the structure may occur, and the error bar value to the same. And then the overload of the section, where the initial question is being talked about is the number of the wall, and the angle transformation, and the angle of projection, and then for that for down the natural height. And he correctly point out the reporter didn't consider the energy transformation between the collision and after the collision. And he called the didn't focus on how well the water affects the result. And in discussion, they discussed about the accuracy of the experimental result and the error bar of the chart and the wire first. And he correctly pointed out the reporter error on the effect of the wire first, and the causing he should focus on the experimental accuracy and not be concerned about the data comparison with the theory. And here the case discussion. But the opponent asked when will the wire flow affect phenomena, and the reporter answered within only the moment when the ping pong ball leaves the water, and I think we think that it will affect the whole system from the beginning. And this is a question. I asked why the reporter used 50 times of the external, but the error bar of the data has the same value at every point. Instead of makes sense. The reporter thinks it isn't important. And then I asked why the data change calling phenomenon. I think the velocity of the container change and will call the pressure rate and have a water jet to push the ping pong ball line. And the reporter thing is boil for and the opponent partially agrees with the reporter. And the next question is, I asked what factor affect the most that the ping pong ball gets the maximum height. I think the velocity of the container drop and the reporter answered the initial height and the opponent is agreeing with the reporter. And thank you.
Continuing remarks from the reporter. So first, we focus on the motion of the ball instead of focusing on the energy. And the main factor affecting the national height according to our theory and our experimental results is the initial height. And we discussed about the opponent discussed about the overall action of buoyant force. And we believe that the return of buoyant force after collision is the main factor affecting this phenomenon. And we forgot to add error bar into the graph. That's our mistake. And the opponent asked about the explanation of our theory, and we're using solving the equations to get the motion of the ball. And the opponent suggests that we can try to get the higher height if we have a better container. But that is the limitations of our experiment. And for our experiment, the too small amount of water will cause the ball to touch the bottom of the cup, and there will therefore be other external force acting on it. And this is out of our focus on this problem. And this is a summary of the discussion. Thank you.
I have a question for the reporter. In your theoretical explanation, you introduce square force. So in the formula, there's a density. So can you identify which density you are considering?
It's the density of air.
Of air.
Yes.
So if without the consideration of drag force, so do you think in the formula at the end, the exponential term will remain or not?
It will not.
And why drag force of air is important?
Because the mass of human ball is relatively small to the drag force acting on it. So the drag force cannot be measured.
So have you checked the drag coefficient of the air and estimate the actual value of the drag force and judge from there whether or not it's important? So,
Yeah.
so I mean you think it's important. So have you identified whether or not it's important? in terms of real values.
drag coefficient.
Yes, drag coefficient and the density of air, for example.
Yeah, it's an effect, so it's important to identify it.
So you did.
Yeah,
Okay, thank you.
that is from yeah, we search the coefficient. Yeah.
You go to your formula. I remember you have a relationship. It's very interesting result. You have a relationship between the final velocity and the rebound velocity.
Oh yeah.
It's like 1 point something.
This one.
So, no, I would like to know the ratio. This is a ratio, right?
Ratio.
Could you maybe most likely no, I'm just curious. It seems like so VT is the final velocity
The terminal velocity.
Okay.
Because there's air drag
of
force.
the car, right?
No, of the ball. We are going to get the maximum height of the ball. So when the ball is in the air, this is the terminal velocity when the ball is in the air.
Do you? So in principle, you can estimate the maximum height.
Yes. Then this is why we have our theory line.
So what's the estimation of the number? Because
So,
you have experiment. Your experiment told me that, for example, you initialize how many, and then you got like I remember 6.5 meters, right?
Yes.
So in principle, you can calculate, right?
yes.
So did you?
Well, so if we put those values inside, the theory line look like this. And because it's an exponential correlation of natural law.
No, this is you measure, right?
Yeah, and this line is from our theory. This orange line is
Oh,
from our
I
theory.
got it.
Yeah.
Oh,
So there will be a maximum value that the height cannot reach.
so the original is simulation from your theory.
Yeah, from that equation.
So for all the case, the ping pong ball is immersed entirely under the water. Have you checked that?
I don't think so, but because for our model we do not have a way to calculate how much it immerses. So and because we know that the boil force is very small, so we just assume
To make sure, so in your model, do you need to assume the ping pong ball is entirely under the water? Is it a necessary assumption? Yes or no?
Yes, I think so.
Thank you.
But I think since all the jurors are asking the question, so it's fair, I have to question for the reviewer. So I think for the opponent, when you see this data, they fit quite well with their theory, but also we think other hydrodynamic forces is also important, right? So in this case, somehow there must be something that is something wrong in his theory, right? So if you think the other hydrodynamic force is quite important, okay, and Laplace is missing from his theory. So in this case, it must be some huge difference between, or at least some difference between his theory and the data, or the experimental data. but somehow it is quite well. So in this case, do you guys still think the other hydrodynamic force is truly important, or there's some missing part in this theory?
I think they talk about where when the ball sticks to the wall of because of the pressure difference, the ball will stick to the wall, which I think that will have an effect in the energy transmission process, which is the reason I think why their height is slightly lower than the exponential.
But almost.
Yes,
Within the error.
yes, but it's slightly lower, which I will explain that.
I see. So how do we?
So this with the energy part, I think he didn't consider the energy loss, and the energy, the origin of the energy loss is from the deformation of the water and air resistance, and whether the container will bounce off. And then if we discuss with the first, I think he didn't consider the air resistance, and maybe when the ping pong ball it gets bounced, it will rotate itself.
Okay. Thank you. Okay. The score for the reporter 76886. The score for the opponent 76777. The score for the reviewer 75654.